push you up. Okay, so I'm going to just briefly remind you of some of the nice aspects of the Higgs mechanism. We went through most of it last Thursday, but I've fixed the notes up a little bit. I thought there was a factor of 2 loose. There wasn't. It was the derivative was with respect to h squared rather than h. In any event, the Higgs sector looks like this. There's the covariant derivative squared of the Higgs field. The Higgs field is a doublet, H plus and H neutral, but it's a complex doublet. The gauge fields are an SU2 that works on left-handed fields and a B that a hypercharge that's a U1 acting on all the fields. For this purpose, all these gauge bosons act on the Higgs doublet. F mu nu is the commutator of 2 covariant derivatives, and then the Higgs term that produces the Higgs mechanism is this funny combination here. The minus sign means, of course, that the Hamiltonian has a plus sign, and so the thing is not bounded below. This gives you the famous Mexican hat potential that sort of looks like this, and the minimum is anywhere here at the bottom of the saucer there. And experiments have shown that this V, which is the value of the Higgs field at its minimum, you choose an arbitrary point here, is 246.22 GeV. The Higgs mass is a little over 125 GeV. And the kinetic action density gives rise to mass terms, which we wrote down last time. And after a certain amount of massaging, the mass terms look like this: minus v squared over 8 g squared a1, that's a 1 mu, a1 mu plus a2 mu, a2 mu plus minus g a3 mu plus g prime b mu times minus g a3 mu plus g prime b mu. And the way we normalize complex bosons is we have a 1 over root 2 and we take a complex linear combination. So for example, we define W plus or minus as 1 over square root of 2 a1 mu, and it turns out it's minus or plus I a2 mu, whoops, mu 2. And what you can see here is that these are mass terms. The canonical mass term for a single scalar field is m squared over 2 v squared, or L equals minus that. This is a mass term for a scalar boson. For a complex boson, it's minus m squared phi squared, like that. And if you use that recipe, you see that the properly normalized fields are 1 over square root of g squared plus g prime squared, g a3 mu minus g prime b mu. And the photon, or the fourth field, there are 4 gauge fields here. There are 3 here and 1 there, but they're not mass eigenstates. The mass eigenstates are the W, the Z, and the photon is then 1 over square root of G squared plus G prime squared times G prime A3 mu plus G mu. This orthogonal combination doesn't occur here. This is W plus squared plus W minus squared. This is Z squared, and there's no A mu term that appears in the mass term, which is this when H is replaced by its mean value in the vacuum. And so what happens is the W and the Z acquire masses, and it's funny, I didn't write down what their masses were. It's curious. I just looked up the other things. The W is around low 80s. The Z is around 90 Chev. So what's nice about, this is the nicest part of the standard model, I would say, because the structure is what's required to support this gauge symmetry, this local gauge invariance under SU2 left and hypercharge. And then the masses turn out to be these masses, and these are all the numbers that are experimentally accessible now, and they all check out. In fact, one of the embarrassing features of physics these days is the standard model agrees with all the experiments, and there's no sign of anything else, and yet it's clear there's got to be other things, because A, this dark matter, and B, the standard model is so silly. I mean, the idea that you have a gauge group that acts on the left-handed quarks and leptons, but not on the right-handed quarks and leptons, is just, in my view, it's just simply absurd. These fields, A1, A2, and A3, you can invert these expressions, and you get that A1, I'm going to leave out the mu's, 1 over square root of 2 W plus W minus. A2 is 1 over I root 2 W plus minus, no, I'm sorry, it's W minus W plus. A3 is 1 over square root of G squared plus G prime squared times G prime A plus GZ. These all have mu's, as I said. B is same square root, and it's GA minus G prime Z. One of the things that I find particularly interesting about this is that the photon that we see every day, because it's how we see anything, is not a simple elementary particle in the traditional sense. Instead, it's a linear combination of 2 gauge fields. One is an SU3 and one is an SU2, and one is a hypercharged field. And that's I think quite interesting. when I said left-handed and right-handed, what I meant was there are these projection operators, a half, 1 plus gamma 5, which is in direct matrix lingo looks like this. P right is the opposite one, 1 minus gamma 5, which is 0, 0, 0, 1. And this is the covariant derivative acting on the Higgs doublet. I might write the Higgs doublet H as H0, H, I'm sorry, it's not H0, it's H plus H0. And, but acting instead on quarks and leptons, d mu looks like this. Okay, there are class notes that are now quite voluminous online. They're around 150 pages that are suitable to read, and then some stuff on gravity that I think is still a work in progress. If we, as usual, define the generators of SU2 as a half times the Pauli matrices, and then have T plus or minus a half sigma 1 plus or minus I sigma 2. If we do that, then this covariant derivative is the identity matrix times d mu plus I g over root 2 W plus mu T plus W minus mu T minus, all that times the left-handed projection operator, plus I over that square root of G squared plus G prime squared, Z mu, G squared T3, left-handed projection operator, minus G prime squared yi, and then plus I G prime over the square root of G squared plus G prime squared, A mu, T3 P left plus yi. So that's what it looks like, and I think, well, let's see. What's clear here is that the coefficient. Well, let's see. Should I? Charge operator is T3, let us say P left, plus yi. And we can see that right here, the thing multiplying the photon field apart from this factor is that. And then this d mu can be finally written as, here, let me just write it, d mu is I ordinary derivative plus I g over root 2 w plus t plus q plus w minus t minus p left plus ig over cosine of the weak mixing angle. That's a thing that involves these square roots. Z mu T3PL minus sine squared beta weak times Q plus IE A mu Q. And this factor here is what goes into making the electric charge E. This is Q, that's E. And I should write down what, let me go over here. Cosine of the weak mixing angle is G over square root of G squared plus G prime squared. And the sine is G prime over the same square root. And, well, I guess it's G prime squared. And the electric charge is G times the sine of theta W. And theta W is around a half. It's 0.50163. So I think that's enough for now. Let me just mention though why it is that I say that the standard model is so obviously incomplete. It's that for left-handed fields, Q is T3 plus Y, and for right-handed fields, Q is equal to just Y. So Q left is that, Q right is that. Or equivalently, you can say Q is this, but T3 is 0 on right-handed field. That's another way of thinking. So what are these values of hypercharge? Well, hypercharge on the left-handed doublets is minus a half. Let me just make sure I got that right. Yes, minus a half for the, well, that's Q left, Y left. Whereas Y right is just all sorts of things. Y right for a neutrino is 0. Y right for an electron is minus 1. Y right for an up quark is 2/3. And Y right for a down quark is minus 1/3. And okay, so these are funny values, and the implications is that the standard model is incomplete, and one needs something else. And I'm just wondering, I remember values of 1 to 6, but my notes are saying these. All right. Anyway, let's switch now to path integrals. I thought we'd start path integrals now. And the path integrals are based basically on Gaussian integration for bosons. For fermions, they're based on Grassmann integration. And both kinds of integration are easier than one would think. Of course, you already know about Gaussian integration. So the basic integral is e to the I a x squared plus 2I dx dx is equal to square root of I pi over a e to the minus I b squared over a. And a related integral e to the minus ax squared plus 2I bx dx is square root of pi over a e to the minus b squared over a. The second integral is your standard Gaussian integral. The first integral is a somewhat non-standard integral, but that's actually the value. And all right, there are matrix values of that which are worth knowing about. Well, you can read about them in the class notes. Yeah.
In the second integral, is there supposed to be an I in front of the B?
I don't think so.
So you have an I in front of the B on the second one and the first one. I was thinking that.
Yeah, we've got three I's and one minus sign.
Okay.
Okay, now, path integrals are also based on something called the Trotter product formula. And let me just write it down for you. E to the a plus b, you can write it as a limit, n goes to infinity, of e to the a over n, e to the b over n to the n. And let me give a physicist's proof of this. Obviously, if a and b commute, this is obviously correct. If a and b don't commute, the term on the left-hand side, is symmetrically ordered with respect to a and b. The term on the right is also symmetrically ordered except for the first term and the last term.
Or what do you mean symmetrically ordered?
I mean that there's no preference for A and over B or B over A.
You mean like you ordered those? It doesn't.
Yeah.
But here it does because they don't commute.
Here it does,
Okay,
but because there are infinitely many factors in the limit, the preference goes away. In other words, the preference is just A over n, of one factor of A over n, one factor of B over n, but even that overstates the preference because the next factor is B over n. So that's the Trotter product formula. So now let me derive path integrals in the case of quantum mechanics, and you might say, well, why not jump immediately to field theory? Well, the reason is that obviously the notation is simpler in quantum mechanics. In fact, I'm going to consider the quantum mechanics of a single particle moving in one dimension in a potential, non-relativistically. But the point is that all bosonic path integrals are natural and simple generalizations of what I'm about to do, apart from a topic, well, as long as the Lagrangian is quadratic in the time derivatives of the coordinates or the field, which is the case for all standard path integrals and standard theories. In these cases, so I'm going to be talking about h equal to p squared over 2m plus v of q. We're going to have a complete set of eigenstates of p and q. And as you know, these are rather unphysical states because they mean that the particle here is precisely at position q prime, and by the uncertainty principle, then its momentum is totally arbitrary, so it really has infinite energy. And over here, the thing has absolutely precise momentum, and consequently, the particle can be absolutely anywhere, and so typically the energy is also infinite because the potential will be that big if v gets far apart, well, in some cases, depending on what the potential is. On the other hand, these are the states that we use for manipulating things in quantum mechanics. The identity operator is an integral QQ dq, and it's also an integral pp dp. So outer products of position or momentum eigenstates integrated give you the identity operator. One more thing that you learn in elementary quantum mechanics is that QP is e to the I, let me get the phase right, QP over h bar divided by a square root of 2 pi h bar. So these are the basic formulas of quantum mechanics. And now, what I'm going to do is I'm going to write let's write the Hamiltonian, which is p squared, well, there it is, so I can just have an equal sign. I'm going to write this as k plus v. And so in fact, I'm going to write this so that this is k plus v times h bar. And that way I can write the time evolution operator e to the minus I ht over h bar as e to the minus I t k plus v, and then I'm going to use the Trotter product formula to write that as e to the minus I epsilon k e to the minus I epsilon v raised to a huge power. I didn't say what epsilon was. Yes, epsilon is going to be t over n, and so this is going to be raised to the power n epsilon. No, n is t over, I'm sorry, t over epsilon. So that's the time evolution operator. E to the minus I th over h bar is going to be e to the minus I epsilon kappa, epsilon k, e to the minus epsilon v raised to the power t over epsilon. Though actually, I'm not going to be using. I'm not going to be using this notation of k and v is just a notational convenience for a couple of equations. So now I'm going to take a matrix element q1 e to the minus I. If we want, we can call it epsilon k e to the minus I epsilon v qa. But this is the same thing as Q1 e to the minus I and T over N B squared over 2M H bar. Remember there's a 1 over H bar. E to the minus I T over N V of Q over H bar QA. So that's the reason I introduced K and V, to not have to write things like T over N and 2M H bar all the time. Well, we can evaluate this. So this is just one factor of Trotter's product formula. Trotter's product formula really has an infinite number of these. And so we're going to do the first one. And so this is equal to, we're going to insert a complete set of states, and we're going to insert it in the middle here. So this is e to the I epsilon p squared over 2m h bar. Insert the identity operator in the form of an integral of outer products of momentum eigenstates. Wow, there's a typo. Now, what's the advantage of this? The advantage is that we have an eigenstate of P here, and we have an eigenstate of Q there. And so this turns into Q1 e to the minus I, an integral minus infinity to plus infinity, minus I epsilon P prime squared over 2m h bar squared, h bar, not h bar squared. E to the minus I epsilon V of QA over h bar. And then we have two inner products. And those two inner products are Q1 P prime QA. And we have a D P prime. And now we know what this is. This is e to the I Q1 P prime. This one is e to the minus I QA P prime, and both are divided by a square root of 2 pi h bar, so the product is that. So what we've got at this point is we can pull out this factor. It's e to the minus I epsilon V of QA over h bar, and integral minus infinity to plus infinity e to the minus I epsilon P prime squared over 2m h bar e to the I Q1 minus QA P prime over h bar dp prime over pi h bar. And by the way, you may wonder why didn't I set h bar to 1? I don't know. I have some self-flagellation complex. Is there a question?
Yeah, so on the equation, not the equation you just wrote, but the one right before that, you have this bra of Q1 out in front of the integral. No, go down, and then to the left. Is that supposed to be there?
Oh, no. That's right. That's gone. That
Okay.
one over here. Okay. You get two cans. Okay, well, this is one of the integrals that I advertised in the beginning. In fact, it's the first integral. And so we can do that integral, and what we find out is that this thing altogether is m over 2 pi I h bar epsilon to the 1/2 e to the I epsilon over h bar m q a dot squared. I have to explain what that is. Minus v of qa. Okay, the v of qa is just this. What is qa dot? Well, this is notation. qa dot is just defined to be q1 minus qa over epsilon. So from the formula over here, the coefficient of x gets squared in the exponential. X here is p prime, and so q1 minus qa gets squared here. And in a sense, you can think of a small epsilon being a small amount of time, which it is, it's t over n, and we're taking, and the next point is q1 minus qa, that's dq over dt, and that's why that, I'm thinking of, that's why it's plausible to call that, or reasonable to call that qa dot. Okay, so that's half of the, not half, but a good fraction of the story of Cahill is what we've gone through. The next part is to put two of these things together. So in other words, Q2 e to the minus I epsilon k e to the minus I epsilon v squared qa, this will then, we're going to use this formula twice, or equivalently first in quantum mechanical terms. We're going to write this as q2 e to the minus I epsilon k e to the minus I epsilon v q1 e to the minus I epsilon k e to the minus I epsilon v qa. And then, in order to make this the identity operator, we have to integrate dq1. So in other words, I'm sticking an identity operator in between these two identical factors. This is the identity operator, the integral over q1 from minus infinity to plus infinity. But now this expression and this expression are both given by this formula, because q1 and qa are just arbitrary eigenstates of the position operator. And so we just use this formula twice, and so what we get is that this thing is equal to this thing squared, essentially. It is then m over 2 pi I h bar epsilon, an integral from minus infinity to plus infinity of e to the I epsilon over h bar times m q1 dot squared over 2 minus v of q1 plus m qa dot squared over 2 minus v of qa. And all that is dq1. Now q1 occurs in two places here. It occurs in qa dot because it is, qa dot is q1 minus qa over epsilon. And it occurs here because q1 dot is q2 minus q1 over epsilon. So this dq1 that we're integrating over occurs twice, and one of the places is, of course, in b of q1. But we're not going to do that integral analytically. We're just going to look at it and realize that we basically finished understanding path integrals, because to get to a full amplitude of e to the minus I ht over h bar, or e to the minus I t k plus b, we need to put together an infinite number of these, and so far we've just put together two of them. But if we put together n of them, well, it would be e to the minus n I epsilon h over h bar qa. What will this be? This will be, by the Trotter product formula, it will be a qb e to the minus I epsilon k e to the minus I epsilon b qn minus 1 dot dot dot, maybe I'll do one of these dot dot dots, qn minus 1 e to the minus I epsilon k e to the minus I epsilon v q n minus 2, and then dot 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 down to q1 e to the minus I epsilon k e to the minus I epsilon b qa, and now we have to integrate d qn minus 1 dq n minus 2 down to dq1. Okay, well, what does that give us? Well, just as the product of two of them gave us this, the product of n of them is going to give us m over 2 pi I h bar epsilon raised to the n over 2. And then it's going to be an integral e to the I epsilon over h bar. And instead of the sum of the two of them, we're going to have a sum j equals 0 to n minus 1, m qj dot squared over 2 minus v of qj maybe I'll put this bracket like that. And then this has to be integrated dqn minus 1 dq1. And now, if we look at that, we see this is dt, or equivalently, if this is the Lagrangian, well, Lagrangian at qj. And so another way of writing this is m over 2 pi I h bar epsilon n over 2 integral e to the I epsilon over h bar, a sum of Lj, j equals 0 to n minus 1, and then times dq n minus 1 down to dq1. Where here L sub j is m over 2 qj dot squared minus v of qj. Okay, well now we can have the insight that Feynman had, I guess, 70 years ago, namely that what we really got here is E minus I, TB minus TA, H over H bar, QA, is an integral e to the I s, the action of the process divided by H bar, dq, S of Q is an integral L of Q dot and Q dt, here from TA to TB, and dq is this factor, m over, well actually it's mn over 2 pi I H bar TB minus TA all that raised to the power n over 2, and it's then dq n minus 1 dq1. So that's basically a derivation then of the Feynman path integral. The time matrix elements and position space of the time evolution operator are an integral over all paths that take you from QA to QB in the time interval TA to TB. The phase of the exponential is the classical action divided by H bar, and then there's this dq is this factor that popped up from the integral times an integral over all the intermediate states, and in the limit of n going to infinity, of course, there are infinitely many of them. Okay. Questions or we can immediately generalize this. If the particle is moving in three-dimensional space, then we would put arrows on these things, and we would integrate here over all of these variables, and there would be a 3n over 2 factor here. And this would be, we just draw arrows over the thing like that, and still it's, so it would look basically like this. So moreover, if there were several particles rather than just one, we'd have to integrate over all of them. The Lagrangian would be a sum over all of them, as well as interaction terms, and we get the same basic picture. Okay, so let me run out of board space, but not out of time. I think I'll erase the board before starting with the whiteboard. Next thing that I want to do is I want to show you why it is that classical mechanics is a consequence of Feynman's path integral. And if we generalize this from quantum mechanics to quantum field theory, it's then why classical field theory is a consequence of Feynman's formulation of quantum field theory. first thing I want to do is consider a macroscopic process. If we have a microscopic process, then basically anything can happen, so there's no sense in which for a microscopic process you can take a classical limit, because a microscopic process isn't a classical process at all. So I have some new dry erase pens which we can try out. Okay. So basically what the Feynman amplitude is it's e to the I s of q, where we're summing over summing or integrating over all processes that take us from an initial, let us say, QA at time TA to QB at time TB. And let us first assume that there is a process that is classical. First of all, that this is macroscopic. So assume the process, this process, is macroscopic, and that there is a path from QATA to QBTB that is stationary. And by stationary, what we mean is, in fancy language, it's at the variational derivative of this, which is to say m q double dot j plus v prime of q is equal to 0. So this is the, in other words, that there is a classical trajectory to go from QA to QB in time interval TA to TB. Well, if there is such a process, then what we know is that the action Q of the stationary or classical process plus dq is the same thing as S of Q classical plus terms of order delta Q classical squared. So in other words, that the whole idea is that the first order variation is 0. In other words, if it's a macroscopic process and there is a classical path to go from QA to QB in the time interval, then that process is satisfy these equations. These equations, Lagrange's equations, are the ones that say that the action is stationary. Stationary means that if you use a small path that also goes from QA at time TA to QB at time TB, but that such that delta Q, the detour, is tiny, always tiny, then the action for the new process, the process with the detour, is the same as the classical action apart from things that are quadratic in the detour. So that's what we're assuming, that is to say that there is a classical process. Well, what that means then is that this amplitude, which is the amplitude for this process to occur, is going to be huge, because it's going to be e to the I s of Q classical approximately times big N, where big N is the number of similar detoured processes. So, in other words, there are a gazillion processes to go from QA-TA to QB-TB. And if there's one that's classical, if this is a classical process, then there are a gazillion ones in which the action is approximately the same. And so the path integral then is approximately the number of such paths times the single phase. And well, obviously the number of such paths is gigantic. And so what this tells you is that if there's a stationary process and the process is macroscopic, then that's how things are going to, the amplitude for that to happen, to go from QA, TA to QB, TB, the amplitude for that to happen is huge. And the amplitude for anything else to happen is correspondingly zilch. And so that anything else to which there is no classical process or stationary process is zilch. And so that tells us that classical physics happens because the amplitudes are huge when there's a stationary process. Now that's all for macroscopic processes. Suppose instead we consider a microscopic process. So a microscopic process to go from here to there. In other words, QA and QB are essentially the same. Well, there, the action for every process is essentially trivial. And consequently, anything can happen, because if we consider the amplitude to go from QA, TA to QC at time TB, where QC is not related to QA by any classical process, still the action is going to be zilch because it's a microscopic process. Because QC and QA are almost identical. So essentially anything can happen on a small scale. So this is why when you get to microscopic physics, quantum mechanics is important because anything can happen. Whereas on classical physics, path integral tells us only classical processes. Okay, all right, so I see that some of you are in fact bored, and so let me get on with the story then. Let's as an example, just to give you more confidence in the reality of what I'm talking about, although just invoking Feynman's name should inspire enormous confidence. Let's consider the case of a free particle, V is equal to 0. Then what does this thing look like? Well, QB, the amplitude QB e to the minus I TH over H bar QA, this turns out to be m over 2 pi I H bar epsilon to the 1/2, no, not 1/2, to the n over 2. And then an integral e to the I m epsilon over 2 H bar. And now this is going to be QB minus QN minus 1 squared over epsilon squared plus dot 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 plus Q1 minus QA squared over epsilon squared. And then this whole thing is to be integrated dQn minus 1 PQ1. Well, it turns out in this particular case, for this integral, because v is 0, you can actually do the integrals with your fingers explicitly. And so to do the first integral, it's just a repeat of the integral. In fact, it's an easy version of one of the integrals we've already done. And you can then see how to do all of them by hand. And what you find is that this is exactly equal to, I mean, if you want, I'll go through the step. They're in the notes, okay, the class notes, which are now voluminous. It turns out to be altogether a square root of m over 2 pi I h bar Tb minus Ta e to the I m QB minus QA, and as I said, you can, this is an analytic calculation, no hand waving, 2h bar TB minus TA. And in 3 dimensions, well, it's the same thing, it's just that you have to cube this thing and you put arrows here. So if you want to do it in 3 dimensions, it looks like that. So that's, and let me remind you all that this, in fact, is the thing, is the amplitude that one gets in ordinary quantum mechanics. The way you get it in ordinary quantum mechanics is you say, well, you've got a QB here. You've got e to the minus I p squared over 2m t over h bar qa, and then you insert a complete set of momentum eigenstates. This turns this immediately into a Gaussian integral of the first form under the clock there, and you just do the integral and you get this immediately. Which do you prefer, blackboard or whiteboard?
Blackboard. Blackboard?
All right. Okay, so let me go to the blackboard now that it's dry. And we've got maybe 11 minutes or so left. So the next topic is path integrals for quadratic actions. And this is, Feynman, of course, was famous for tricks. When he was in the Manhattan Project at Los Alamos, he, for example, would pick the safe that contained all the classified information and all the secrets and leave a note inside for General Groves. Which drove General Groves crazy. I guess, I don't know, I wasn't there, but that's the story anyway. So let's again consider the case where we have a path that's the classical path plus a detour. And I'm calling the detour now x of t. And x is a path that x of, let's see, do I call it 0 or am I still TA? All right, x of TA is 0, x of TB is 0. That's because we want the new path to go from Q8 at time TA to QB at time TB, and consequently the detour must vanish at the endpoints. And I'm continuing to assume, of course, that the Lagrangian is quadratic in the time derivatives, but also now I'm assuming that the potential is quadratic in the coordinates. And so this action S of QC plus X is going to be an integral TA to TB, a half m q dot squared minus b of q dt, and we're going to be able to expand that, and of course the expansion is TA TB a half q dot plus x dot q classical dot plus x dot squared minus b of q classical plus x dt. And now when you expand this in powers of x and x dot, you can throw away the linear term in x, because QC is a classical path, where I'm assuming that a classical path exists to get us from QA to QB in the time interval in question. And so what we get then is the quadratic part, integral TA TB of m over 2 q classical dot squared minus b of q classical plus integral TA to TB, well, dt, hold on. Plus integral TA to TB m over 2 q dot squared minus b double prime, and now that's just q classical over 2 x squared, and then higher terms, minus b triple prime of q classical x cubed over 6, and so forth, minus fourth derivative of q classical over 24, x to the 4th, minus dot 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 dt. Okay. And so we can write this as s of q classical plus delta s of q classical and x. Okay. Now, the point is that this v double prime is actually independent of q classical. I wrote parentheses q classical, but in fact, actually this, what I've written so far is generally true, whether or not QV is quadratic or not. But if V is quadratic, then V double prime is independent of Q classical. In other words, V double prime just depends upon the parameters of the theory. And is independent, so V double prime, V triple prime are independent of the classical path Q classical. And so in other words, delta S of Q classical and X is just delta S of X, which is an integral TA to TB of 1/2 m x dot squared minus a half b double prime x squared dt, and of course these are xt's. So this extra term here is just a function of the detour, and the detour is a loop. it goes from 0 to 0 in the time interval, TA to TB. And B double prime involves, it depends upon the parameters of the Hamiltonian or the action or the Lagrangian, but it's independent of the classical path. And what this means then is that the actual amplitude, which is QB e to the minus I, QB minus TA Hamiltonian over H bar QA, this is going to be an integral, a path integral EPI S of Q classical over H bar plus I delta S of X over H bar dq, but dq is just dx. And so this is actually e to the I S Q classical over H bar times e to the I delta S of X over H bar dx from TA to TB. So this is a phase of the classical action in units of H bar. This thing is something that depends upon the time interval. It depends upon the parameters of the theory, but it's independent of the classical path. And so what this means is that if the this thing is a function just of time, or of the two times, TA and TB, and the various parameters of the theory, and then times e to the I classical action over H bar. So in other words, if you have in other words, the amplitude for a process is a factor, it factorizes into something that's a function of the time interval times a simple factor of the classical action to go from the initial to the final state. Now, of course, if there is no path to go, classically, to go from the initial state to the final state, then this analysis doesn't work because we don't have this classical path to approximate around. And so this term would be meaningless. But when it is meaningful, that's what, in other words, the whole path integral is a function of time times a phase. And so that, but again, this is for for theories that are quadratic, like harmonic oscillator, free particle, and then anything else that's quadratic. Quadratic, of course, means it could have a linear term. All right, well, let's see, I think we're out of time. Is there... I guess we might as well stop because, well, all right, I don't know. If you guys want to hang around, I could, another topic is Bohm and Haranoff, but maybe we just leave that for Thursday, I think. Yeah. All right.